Hi and welcome to another lesson about x86 architecture. This time we are going to talk about the first few instructions that you are going to study. Objectives of this lesson. You will learn about some basic x86 instructions. For example, basic data manipulation will be done with the instruction move. Simple arithmetic. We will learn about the two instructions add and sub. Basic instruction structure. x86 instructions have numeric representation, opcode, and textual representation. x86 instructions have the following structure: mnemonic or shortcut for the instruction's name, and arguments, which are needed for the operation. Every instruction has both a numeric representation, which is the representation that a processor can understand, and another representation which is textual. The textual representation is for us humans to see and to look at. It is much easier, at least for me, to use the textual representation to write the instructions. It is written like this: mnemonic, which is usually something pretty short, usually made of only 3 letters or 4 letters, and then the arguments of the instruction. Usually there are no more than 2 arguments. Sometimes even there are no arguments at all in some instructions. We are going to see this kind of instructions too. And they are separated by commas. The arguments are somehow encoded into the numeric representation. You might wonder, how does these arguments get inside the numeric representation, the base 16 representation, or the base 2 representation, the binary one? Mostly they are just encoded somehow. Sometimes the arguments are maybe registers or numbers. They just fit inside the encoding of the instruction. Maybe we are going to see this a bit later. Encoding instructions. There is a computer program that translates the textual representation of an instruction into the numeric representation of the instruction. This program is called assembler. While the numeric representation is unique and agreed upon, there are different textual flavors or syntaxes to represent the instructions. We are going to use the syntax of the FASEM flat assembler. We will learn more about it later in detail. Mostly you just have to remember that you don't have to convert the textual representation to the numeric representation yourself. There is a program that can do it, and it's a very nice program. There are many programs that can do this conversion, and they are called assemblers. We are going to look at a very specific syntax, textual syntax, to convert to the numeric representation, and this will be the syntax of FASEM. FASEM is known as the flat assembler, and it is a very common assembler these days. It is also very easy to begin with. We are going to speak much about it later. For now, just remember that we are going to use mostly this syntax. The first opcode or instruction that we are going to talk about is move. Move allows us to move data. Strictly speaking, it allows us to copy data. It has those arguments: destination and source. And what it does, it copies the contents of source into destination. The arguments themselves could be many things. For example, they could be registers, or maybe the source could be even just a literal number. We could put a number in here. And they can even be places in memory. We are going to speak about the ability to use memory arguments later. Now we are mostly going to use registers and just numeric literals. Some examples. Move EAX 8CB. Let's look at this example. This is going to put the number 8CB inside EAX. You might be wondering, what is this H thing here? H in the FASM syntax means read this number as base 16, which means that the assembler will know to regard this number as base 16, and it could convert it to other forms, maybe to binary later. Move ECX EDX. This instruction will copy the contents of EDX into ECX. Move SICX. This will copy the number inside CX into SI. And note that this is a 16-bit data copy. The last instruction, move ECX EDX, was 32-bit copy. Not like this one, which is only 16. Also note that the source and the destination in this instruction have the same size. This is very important. In move instruction, the source and the destination must have the same size. This is 16-bit size, and here we have 32 bits size. Example for trying to do something wrong. Move 13 ECX. There is no such instruction. First, if we try to logically think about it, it is kind of strange. We are trying to put ECX inside 13. What would it mean? It is not possible to assign ECX into 13. And maybe strictly speaking, there is no numeric representation for this kind of instruction. The assembler won't be able to translate this text into the numeric representation of move, because there is no such numeric representation to represent this. Another invalid example, move ECX DH. What's the problem here? ECX is of size 32 bits, however DH is only of size 8 bits. The sizes don't match. There is no such instruction. The assembler won't be able to assemble this text into the right encoding, because there is no such encoding. Let's look at an example of how move works. We make a table of the effects of various move instructions on EAX, ECX, and EDX. I mark here with question marks the fact that initially we don't know what's inside EAX, ECX, and EDX. Note that there is always something in EAX, ECX, and EDX. There is always something in there. Every bit in all of those registers must be 0 or 1. There is no such thing as question mark in the real world in the processor. We just use it here so you understand that initially there was some value inside EAX, maybe from previous calculation that we don't know about. And also know that here we only look on EAX, ECX, and EDX. There are more registers, we just don't look at them right now. We try to focus on these 3 registers. So the first instruction is move EAX 3. That is going to put the number 3 inside EAX. We can see that 3 was put inside EAX. The next instruction, move EDX AB. This is going to put AB inside EDX, which is just what happened. Now another instruction, move EDX EDX. This is going to take the contents of EDX and assign it to EDX, which is mostly going to do nothing. The value of EDX is not going to change. We can see that nothing happened here. I think it's a good demonstration that you can do weird things if you want to. Move ECX EDX. That will take the value inside EDX and copy it inside ECX. It copied the AB inside ECX. The last one, move EDX, EAX. This is going to copy the contents of EAX into EDX. Note that the previous value, AB, was overridden with the new value, 3. Another example regarding the move instruction. This time we make a table of the effects of various move instructions on EAX, ECX, and their partial counterparts. Again, we assume that we don't know the initial values of EAX and ECX, and we mark it by question marks. I remind you that there is something in EAX and ECX, we just don't know what it is. So we begin with the first instruction. The first instruction copies the value 9C into AX. And we get this result. Take some time to look at this result. The higher part of the highest 16 bits is still unknown for us. We don't know what is in there. However, we now know for sure the lowest 16 bits. They must be 009C in base 16. And that is because AX is of size 16 bits. And when we wrote 9C inside of it, we overridden this part. The next instruction is going to be the copying of this value, DDDD1234, into EAX. This is going to override the previous value that we put inside EAX. The next instruction is going to assign the value E5 into CL. I remind you that CL is the lowest part of ECX, the lowest 8 bits. And we get this result. The last instruction is mostly interesting. We are going to copy the value of CL, which is this, the lowest part of ECX, the lowest 8 bits, or maybe the lowest 2 nibbles. We are going to copy it into AH, which is this part, the 1, 2. We are going to copy it into those 2 nibbles. And we get this result. This is interesting. Just to be reminded, this part, E5, is actually AH. This is the picture that we used to have about what consists EAX. Half of EAX is AX, the lowest 16 bits, and AX itself is made of 16 bits, which are separated to 8 and 8. 8 bits to go for AH and 8 bits for AL. So this part, E5, is exactly AH. When we moved CL into AH, we got that we copied this value, E5, into here, instead of 1, 2.